what I did, what's that?
I thought I was gonna be late today, so I got you a birthday cake pop while I was waiting for it.
And then you're on time?
And I was on time.
That's a treat for you.
You can still have it though. I thought I saw that.
I don't like super much.
Oh, okay. All
But
right.
I appreciate the offer.
Yeah. It was
I'm
more.
a savory type of man, you know what I'm saying?
That's fair. Okay. We'll go for this. Weird being on time.
Oh, get used to it. Get used to it. I hate it. Ready? What do you mean?
Got here, bro.
Let's go. I woke up with a little bit more energy than normal today, so it's all your fault.
That's fair. That's fair.
Or not your fault, sorry, your problem. It's your problem now. So I've done things this morning that I normally don't. Like prepare for class.
That's awesome. Yeah. No, but I mean, you know, you're having a good day. Yeah. Been a whirlwind. Yeah. Hopefully you can see it straight. Air out this cake pop right now. There's no trash. Do you want a cake pop? It was for him, but he doesn't like sweets. Sure, I'll take it. Well,
Go down cake poponomics.
No, exactly. Practice is going on.
Read. You don't even live far. What do you eat a full breakfast before you get here?
I'm sorry about this is that.
So college student. I think somewhere along the line, I think it must have been. Yeah, it must have been somewhere in undergrad. I decided that I was gonna remove all of the doubt associated with picking a breakfast.
yeah.
And so I just eat the same breakfast every day for like 17 years. So, you know, it's easy. You just
Yeah.
do one thing and then you ever fix it again.
What if you get tired of it?
I haven't yet. The only time that I don't eat that is when I'm in a rush.
What
Okay,
is it?
well, it's 10:30. We're gonna
What's
start.
breakfast that you're eating?
Oh, breakfast energy? Is that what you said?
There's a water-
I said, what's the breakfast? The same breakfast.
I guess you have to find out. End of the semester treat if you make it that far. It's the breakfast of Mateo. It doesn't do anything special, but. So if you've looked online in the past 5 minutes, you may have noticed that one of the tasks that I went through today is I kind of mapped out the remainder of the course. And I wanted to see how much time I wanted to spend on each of the remaining topics. And, you know, the next 2 sets of topics is what I'm the most confident that we'll be able to get done in the time that I've allotted. But of course, I'm not gonna hold myself to anything like that, because if you guys wanna spend more or less time on any of it, just be like, you know, the symbol. Here, speed it up, and then it says slow down, right?
Okay.
Okay, so we'll talk a little bit more about how light propagates, in particular through matter is what we'll talk about today. We'll talk about absorption and transmission, which are things that you'll need for any sort of radiative transfer that you'll ever do. So for example, if you like video games, you don't like video games? You like video games? You know Red Dead Redemption?
Yes.
Ever heard of this before? Classic game. Okay, Red Dead Redemption 2 is famous because you know you just go around with your horse and it looks really sick, and then you like shoot a snake or whatever. Okay. One of the things that's the most amazing about Red Dead Redemption is that as you go around, there's weather and there's fog and the water, like you know, the sun sparkles off the water. Why does that look so realistic? It's because of a modern understanding and interpretation of radiative transfer. So we'll talk about the very basics of how they can do this so well in a computer game. Understanding that in the future, if you want to go into video game development, you will have to understand scattering properties super well. Yeah.
Is that what ray tracing?
What?
Ray tracing?
Yes, well, ray tracing is ray tracing, but we talk about an individual ray coming in, and then what it does, it scatters through the medium, and then it moves through. That entire process is called radiative transfer. But yeah, they share the same RT. So when you go to grad school, for example, you learn RT, radiative transfer. And then when you get hired by Ubisoft or Blizzard for like 7 times the salary of anyone who is gonna graduate, then they call it ray tracing. Does that make sense? Okay, so it sounds like this is super boring and it's not useful at all, but you may end up doing it for the rest of your life. Because, you know, thinking about graphics, thinking about visual effects, doing that well, and especially when we talk about, you know, if you look at CGI in the past 20 years, how has it gotten better? Well, yes, obviously Shrek now has a more contoured Shrek face, but one of the main things that you can tell the difference between older CGIs and now is how well light scatters off of an unsharp medium. So they do metal really well, right? Uniform scattering. Non-uniform scattering off of a face is really hard to do, right? So in the next 20 years, if you want to be really good at it, you have to understand what we're going to learn in the next 3 weeks. Okay, so that's the next 3 weeks. And then we have this thing called exam. So there's another one. So you will have to decide again whether you want exam or you want to talk to me. Okay, sick. So tell me beforehand. And then we will do radiation. And you might be thinking to yourself, wait, aren't we doing radiation? No. We're going to be talking about the interaction of light specifically through matter. So far what we've talked about is the matter and the fields that it creates. We'll talk about how an electromagnetic wave is going to interact generally with mediums. And then we'll sort of open that box, we'll look really deeply into it, and we'll see what is happening inside of or near atoms and molecules to make them be able to bounce light, absorb light, etc. So that'll be radiation. And then I think I go to Tokyo. So there will be one class that I miss. So I can either have someone fill in or you can be like, I don't want to do this. So it'll be another choice that you get to make. What? You want PK to do it? We could ask PK.
Okay.
Yeah, he would be maybe interested. He may have a class at this time now. We have to see about overlap. It has to be someone who doesn't have overlap with this class. And then we'll end on special relativity. And we'll go back to the reason why this is so fascinating in the first place and how someone sitting on a train looking at a clock tower can revolutionize the world. That's Einstein going to work in the morning. Okay. Questions, comments, concerns? Okay, no homework this week, but we're gonna start homework again next week. And I'll be giving you back a lot of written work. I'm hoping you're still doing it. I think it's due this week. Okay, so what was the last thing we talked about?
Oh, light carries momentum.
Light carried momentum, very good. And then we had this sort of like tirade about how, well, if light carries momentum, you could build like a sail, you can go flying.
Ray
Cool,
causes
right?
pressure.
Like-
Like Treasure Planet,
What?
Treasure Planet.
Like exactly like Treasure Planet, but for real.
But for real.
That was good.
Well, the only thing that's inaccurate with Treasure Planet is that they are like on a spaceship, but they're like out in space, like walking around on the deck, like it's anti-gravity or something.
The pirate.
Yeah, the pirates, if they had little helmets on, I would have been okay with it. But everything else was inaccurate. Okay, so we said that, for example, you may have like a rock or sail, and then just in a vacuum, light goes and bounces into this, right? And it transfers the momentum or the energy that it had into the object. It does that for perfect absorbers, right? Something that takes in all of the light. And so we have this idea that white, or something that is very high albedo, very reflective, bounces the light off of it, whereas the true idea of black is something that absorbs all the light. So in a perfect world, a perfect absorber would take all of the light. Okay? And the question we have to say is, well, what happens if you don't have a perfect absorber? Because we can see around us, nothing here is a perfect absorber. Everything is doing a little bit of reflection, right? Okay. So we're basically gonna start using these ideas to understand what happens when light. Currently, we're looking through a matter right now. What matter are we looking through?
Air.
Air, good, what else?
Fluids?
Yeah, our eyes themselves, like there's like a fluid in it.
Yeah, there's a fluid that you're looking through that is inside of your eyeball. And then, like you said, your cornea itself, the lens, is another piece of material. So all of this light is moving through material. But generally speaking, the type of work that we're gonna look at, we have to say, well, do the waves propagate through that? Do they?
I feel like they should.
They should, right? Because
Yeah.
we are seeing. Okay, all right. Well, most of us are seeing. Okay, so let's write a few things down. Okay. So inside of matter, where there's no free charge, there's no free currents, we're gonna write Maxwell's laws. Okay. Remember this one?
Oh, crap. Yeah,
You know,
No, you don't have to. You don't have to go anywhere.
there's a.
What did this mean?
That's like.
Displacement what?
E,
Field?
Field.
It's the
Yeah.
field of displacement, and we think about it in the context of what two fields put together, sort of. E, correct, which is the electric field, and
so the E field made by the matter or something like that?
yeah, kind of a way of thinking about that, right? It's we call it the polarization field, which is the response to the E field. So the total here was the displacement field, right?
Yeah.
And in the absence of any free charge or any free current, what is it equal to? Correct.
Those guys.
It's a good guess. All right, what about this one? Correct, always. Always and forever. What does that say?
No sources of steam.
Of,
Magnetic. field.
of B. Okay, so there's no point charges of B. Now, there can be sort of things when we think about it in the context of like a magnet. You can say, well, that is a source of north, but it also is a source of south, right? Okay. What about this one? What about this one?
Had like a bunch of stuff in it.
This one doesn't have a muon because it has H.
Oh, or is it
Like, something B minus M.
yeah, or it has to do with the magnetization.
Look at the symmetry here. The hint of the symmetry.
Oh, this is
So
like
E and then
the partial of what? No. Is it?
Then also.
Is it E?
is it D?
Okay, let's try.
T.
Stop.
I like D, E, T. That's what I think I heard. A B.
E, oh, B, what? Oh,
Oh, it didn't, okay. No. Okay, so what does this one mean? It says the curl of the auxiliary field, or the field that is given rise to due to magnetization plus E fields, is due to the rate of change of the displacement field. Right, the displacement field again is the electric field plus polarization. Okay. And if we assume that the medium linear, then we can also say that D, just make sure I write this right. Epsilon of the medium, U, H. 1/mu. So if this is true, the medium is linear and homogeneous. Then you will get your same wave equations, your same Maxwell equations that we started with. Del dot E equals del E equals 0. I know that's a disgusting way to write it, but it's fine for this. Okay. Del dot E or B. Maybe I should just write it on. So. Gonna try and like simplify it. Whoop-de-doo. What did we do?
Pretty nice setup for like, initial conditions, so.
Of what? So let's think about what we're doing. I'm asking for Maxwell's equations in a medium that is linear homogeneous. So imagine this room, but we're not in it. It's just air, it's just water, or it's just some dielectric. And there's no free current and there's no free charge. Okay.
What does it mean that it's linear? Does it just mean it's like?
It means that it satisfies this relationship.
Okay.
So there are some non-linear mediums where the D is not, or if you think about the way that the polarization occurs, it doesn't occur this way. So that's a command, not a.
So I meant like a line, like the room is a line.
Oh, no, sorry. The physical property is that it's a linear dielectric. Okay, so what did we find out?
I guess now we can describe light in this environment.
Light?
Uh,
I've never even once said the word light. Not
the moment.
so how do you know that this is light? How do you know that this is light?
Well, I know that like we have an E and a B component of light inside of it, so I'm seeing it both. So that makes me,
E and B together means light.
yeah,
But I have E's and B's for like charges and a capacitor.
sure. But there's no free charge. So there's like none of that moving around. Okay.
You have that?
It's also like, you need that they're being crossed by like, Del.
So you like that because that looked like S from before.
Yeah.
Okay, does this equation look similar?
They all look kind of the same.
Okay, you're just glazing at like 8 weeks. You're like, they're all exactly the same.
How is this different from all the other ones?
That's the question. That's what I'm asking. So up there, we wrote Maxwell's equations inside of a medium. And then we used some properties of them to write them this way. Does this look like anything we've done before?
Why are we bringing the H and the D back?
You put it with that.
Yeah, okay, so this is so let's start again.
Okay.
Okay, I wrote everything down and let's figure out why I did it. So we're in this room. I would now like to describe what solutions for the electric and the magnetic field are possible in a room in which I can, if I want to, polarize and magnetize parts of it. So in this room, there's a medium. Okay, you feel it? Okay, so that medium can be polarized, that medium can be magnified. Okay, so now what solutions for E and M are valid according to Maxwell's laws without any free charge?
They all look the same, there's no other J's.
Good, yeah, they look the same, there's no J's, there's no rows.
No curve.
It's not the same, there's a slight difference, one tiny baby difference. I thought you would notice this first since you said it yesterday. Or not yesterday, Tuesday?
Right?
Friday, no, it's Tuesday. Okay, so these look like the equations we just did, which were wave equations.
Oh, okay.
You remember that?
But they were square waves.
Yeah, how did I do that? How did I make them squared?
Oh, you can't square it, huh?
You just took it in the del.
No, I took a del cross of this.
Yeah.
Right, and then I took a del cross of this,
Oh.
and then I used those identities. To move them around, and I got, del squared of E equals ddt squared of something.
Yeah.
Right, and then so on and so forth. But this is where I started, except for this. You notice there's no knots on it?
Yeah.
No. I love that, but no. In fact, I didn't forget, and this is the only thing that's really important to notice here. Is that the permeability of the space, the magnetic polarizability of the space shows up here in the same place before that we said that the V is going to show up.
Is it not? Is it not knots because it's like a vacuum?
There's no longer a vacuum.
No.
Yeah, the knots are in a vacuum. So when
Oh,
we were thinking about propagating in outer space, we could get the full speed of light. Make sense? Okay. So in fact, we can now say that V in any medium
This is not frequency, this is actually speed.
yeah, that's a V.
Okay. Your
Yeah.
frequency looks like,
Like this one?
yeah, come on.
That looks so different. There's no little finger on the side.
Now they look the same, now,
Now-
by adding that.
I'm not gonna add the finger though. I'm very good at not doing that. Okay. That makes sense? Okay. So this is great. This is really straightforward. Because you may have even seen this before. We can think about this type of an equation. Maybe you try 2500 or 2510. And one of the very first things you learned about light was how it's supposed to go through different mediums. You have to do all these really silly problems about, how far is the ball if it looks like it's over there, right? But it's in the pool.
Yeah.
Is it closer or farther to you?
Yeah.
Okay, what about you like take a pencil, you like have a cup of water, and you like put it in the cup of water and it looks it goes like that?
you learned that?
Yeah, it was like a diffraction.
Maybe you didn't. Okay, so what did you just say?
Diffraction.
Diffraction. So now the question is, can we derive diffraction from first principles? From these equations? Yeah, we're gonna. So that's where we're headed. And the very first thing that you learned, there's one law you learned, do you remember? About light, you're right, about
Yeah.
light.
It's always constant. Like
Speed?
it'll never.
It's got a name and then law.
Speed
Name
of
law.
light.
Name law. Named after a small animal you find in the garden.
Really?
Snake law.
Close.
Oh, Snell's.
Snell's
Oh,
law.
Snell's law.
What's
Like
this
snail
now?
law. No, okay, alright.
Yeah,
Stop.
there's like a
Don't even look at me.
land.
Alright. Alright, so Snell's law talks about something called the index of refraction.
That's right.
And we told you things like the index of refraction for space is 1. And you were like, cool, whatever, don't care. And then we said the index of refraction goes up with more mediums that make the speed of light go down. You remember this? So like, for example, air, it's something like 1.01 or something. And then for glass, it's something I think like 1.3. Plexiglass, it's like higher, 1.5. And you're reducing the speed of light. That was the claim. So in fact, this is how it happens. This is the permittivity and the polarizability of the material. And we can write them in terms of the speed of light. So we could say that this would be equal to square root of mu naught epsilon naught. That's not an epsilon. Over times c. That's the speed of light, because those are equal to the same. I just multiplied by one and over the other. Right? C over c. Okay. Or we could write this as c over n. This index. Wow, sick. That's so cool. I'm so glad I came to class today. Right? Right? Okay. So what is n? How do I write n?
Like a ratio.
You can tell me. You can read it out.
Oh, just write it that way, C over D.
Oh, no. What is n? Not c.
What is it?
Like number index of perfection.
Very good. How do you write it?
It is in like the medium you're in.
Yes, depending on the medium. So we want to write it in terms of, say, permittivity of free space and the permissivity of the material. So what would that be?
It's simple as rewriting.
What?
Yeah, E over.
Yes.
Oh, okay, cool.
All right.
Nice.
And
That's it. That's an N.
That's
that's a mu.
Okay. Well,
Okay, come on now.
context clues again.
Is that better?
that's what.
They're all M's, it's just the Greek M. Okay. You know, it's like I'm gonna start using emojis. There, your kids will get it. Right?
Okay.
So this is N. So let's think about what these mu's can be. If mu is equal to mu naught, and epsilon is equal to epsilon naught.
Are those two C's the same?
Yes.
Oh,
Yeah. Yeah, this is the.
That's supposed to be mu naught epsilon naught on the top. Or on the bottom. Supposed to be the same.
Okay, cool.
Thanks. Yeah. Good. Teamwork makes the dream, right? Okay. So if mu naught is equal to, sorry, if mu is equal to mu naught, what? If epsilon is equal to epsilon naught, 1. And n is 1. And the speed of light in that medium?
C.
C. Good. So you're traveling at free, you know, as fast as you can. No speed limit. Okay. So now you go into a medium. Can mu ever be less than 1? Or sorry, can mu ever be less than mu naught?
No.
No. So it's always a number greater than mu naught. So let's say it's like 1.5. So now this number is greater than 1. Even if this one happened to be 1, now n is going to be a number greater than 1. So you can never get a medium in which n is less than 1, and it only can get larger. That make sense? Okay. Okay, so what happens when light, light's going from one direction? Let's say it passes from one medium into another medium. So let's use, for example, there's a window, right? I can see a beautiful day outside. Okay. So light is gonna go towards the window. And we need to maintain some boundary conditions. So that it is not discontinuity, there's no discontinuities in certain fields. Okay. The perpendicular, wow, not gonna work. Ugh, draw a little picture. Okay, so this will be medium 1 and medium 2. Okay, we're gonna have light come in from that direction. And if we recall, you might have E say going up, propagation direction is this way. Okay, let's say this is the direction of E, then B is coming out perpendicular, right? Does it matter the orientation? Well, not now, but yeah, eventually. So like we use sunglasses, everyone use sunglasses, and then sometimes you tilt your head, it like looks different. That's called polarization. We'll talk about why that is. So that's the orientation of the E and E fields. So if E is coming in like that, you can use a polarizer to absorb it, so you get less light. Pretty cool, right? That was good. I like that response. Okay. So let's think about boundary conditions for a moment here. So in fact, I can write E1 perpendicular is equal to E2 perpendicular. So what does that say?
Perpendicular, meaning like perpendicular.
Perpendicular.
It's the component. Yeah, so if we think about it in terms of a parallel component and a perpendicular component, they need to match. Right? So think about let's say I have some medium like this. Okay. There will be, if there's a vector, let's say there's a vector like this. Okay, and that vector, it's the medium. There is both a perpendicular part of the vector and a parallel part of the vector. So I can separate any vector into its perpendicular and its parallel components, right? Because I don't really care about the orientation of the coordinate system currently. I think if I put X's and Y's in here, look, you die. Okay. We're just gonna separate them. Because it'll be fine, I promise. Okay.
You're not care about this right now.
Definitely not. Please. We'll do that later. All right. And so in fact, B1 needs to be perpendicular with B2. This. And the parallel components here, I can write E1 is going to be equal to 2 and 1 over mu naught, or sorry, mu 1. I think there's a better derivation of this in the book. Maybe they just stated it. Yes, this is derived in chapter 7, equation 765. We're just gonna accept it as true. Because sometimes derivations in class are not as predictable as we want it to be. But instead, let's choose some solutions here, okay? So we're gonna start with what we call normal incidence. So let's imagine the wave is traveling like my picture. It's not coming in at any angle, okay? And we've already claimed that we have wave equations. So now I'm gonna be able to say garbage like, well, E equals something, right? Okay, so let's start off on the left-hand side, medium 1, and let's imagine that we're gonna write our starting wave. Okay, on the right-hand side, we have an expectation in wave 2 or in medium 2. We have another expectation that we'll have another wave. And we want to know how are they connected? What do they look like? Okay. So first, E1. What is E1? What? Yes, in medium one.
It's fine.
It's a sign, okay, so it's a something, right, okay. I'm gonna go with this one. Just because I don't wanna deal with the sign because. Not that you're wrong, but I'm sure.
KT
K T
or KW.
K W
Oh crap.
KZ.
KZ, there
There it is.
okay,
Minus
and we said KZ because,
That's like the direction that we chose for the light traveling.
Yeah, you tell me. It's going to the right.
Yeah.
Because I drew it this way, it has to be right. Okay, and also matches my notes. Okay. And next,
Omega.
all right, are we missing anything really important?
Amplitude.
Yeah, the amplitude. So we're gonna do some complicated amplitude math here. Okay, that would be 1, 0.
Amplitude's 10.
Yeah, no, 1, 0. Okay. It's not 10, it's 1, 0. Is that okay, or do you want to do something different?
We can do like a comma between it.
Oh.
You have to write the comment.
And which direction is this going, by the way?
The right direction.
Is it?
Oh, I guess like it's broken up in parallel and perpendicular. Is that how you want us to think about it?
Yeah,
Propagating like outward, so like moving in this direction.
right. So it's propagating in the z direction, but it's fully confined in one direction. And that has to be perpendicular to B,
Yes.
right? That's what we chose. In order to propagate waves, they have to be like this, and the third one has to go like that. So we have E, B, Z, like that. In fact, that's what I drew here, no? So E, the vector E, has to be in which direction if we want to use letters?
The up down Z direction.
You're saying Z, so Z would be that way.
Okay, I guess like E direction. The plane, how about that? The,
Yeah, let's say we wanted to use X, Y, Z.
Okay, then it would be the XY plane. Oh, sorry. Hang on, wait a minute.
What do you like?
What?
Why Y hat?
There we go, there we go. That's what it
Okay,
is.
okay, so we just say one or the other,
Got it.
not X, Y plane, because it's only in the X plane,
Yeah,
right? It actually stretches in the X Z plane because it starts in X
there you go.
and it propagates in Z. And similarly, what would the B do? And then we'd have to flip over
That would be like the YZ.
the Y Z plane.
Okay.
So let's do that. Awesome.
Nice.
Okay, what about B? This one's really tricky.
It's like the same thing, but.
That's correct. In fact, I'm going to rewrite B in terms of E. Just so that I can make this choice a ton of times. I'm gonna write it like this. Okay. What goes here? Okay, you're not worried that it has to be different?
No, it's still the right direction, yeah.
And which direction are we going here? Which hat? Whew, that wasn't so painful.
Done.
Now we've learned it all. No, just kidding. Not even close. Okay. So we have this is not the right hand. But I'm just saying, we have, say, X, this direction, which is where E is oriented, B is going out in this direction, and it's propagating. And so, it's doing this, right?
Yeah,
I can't get my fingers to go through to the other side, but this would go down, and this would go over, and then they'd go back, right? And they're in sync.
Yeah.
Right, so E and B are in sync as they travel. Okay. All right. So what would happen though if the wave reflected? Negative KZ. Very good. So this would probably change, you know, we'd have to do some modification, but inside the wave, K would go to minus K. Right? So you might say to yourself, well, what if you have a reflected wave? I'm really bad at board space management. I apologize if it's really hard to keep notes with.
It's all right.
Don't write that on my slip, I know it's a problem.
Yes.
You don't even pull those out, it's okay. Alright, here we go. So if you have a reflected wave, ER. Okay, that's gonna be your original O, but the reflected. And then what did you say? How do we go through?
It would just be moving left instead. It's like a rope that's attached to it, and it would snap back.
Right, so it's going back in the other direction.
Yeah. Like that.
So the velocity is gonna change direction. But it's not required to change for E. Okay. The velocity changes direction. So what's gonna happen to the V here? If I look at V reflected. We do the C down here on the bottom. V is gonna go to minus V. So let's go, and we'll write in here 1 over V. And now I'm gonna put a minus sign, very small, you can see it.
Yeah, or like subscript skin.
They're gonna be bad. Lots of letters and we have to work on them afterwards. Okay, so that's the minus I.
Looks like we're spelling the order.
Yeah, the harder, the more math you do.
Right messages to
The more that it feels like it's not even math anymore, it's like, does that work? Okay, cool. Now we understand reflection. Awesome. Okay. What about the transmitted wave, the one that goes into the boundary?
It's like a
Question. K would still be negative, right? Or is that the velocity?
I think it.
We're gonna match the Ks here, and we're gonna talk about how Ks change in transmitted versus non-transmitted waves. Right now, we're just leaving it as a variable, and we're gonna see what happens to it. Right? We know intuitively that it'll have to end up negative, but will it change how big it is? Right? Will it speed up? Will it slow down? Right? That's the thing that we're gonna find out. And in particular, we're gonna see as we go into a new medium, how does K change? How does omega change? Right? Those are the questions we want to ask ourselves. Okay. So what about the one that goes into the medium?
Like a fraction of what it originally started with, depending on.
Sure, yeah, that's how we physically understand it. What about the wave itself? Is it going to suddenly go off in a different direction or
Could.
in normal incidence?
Oh, I guess not. No.
At normal incidence, we have no reason yet. Right? At a sloped incidence, we'll have to figure out Snell's law from first principles.
Right.
But at normal incidence, we have no expectation that anything should change. Right? So it's gonna keep going in this direction, and we're gonna hope, you know, according to our boundaries. The boundary conditions here, keeps going in this way. Okay. So let's see what we can find out about the amplitudes. Okay, so I said over here, the parallel component of E1 has to be equal to the parallel component of E2. Also a claim down here, 1 over mu naught of E1 equal to 1 over mu naught of E2. That's no. Okay. You said that that need to be a smaller fraction? Could be, because we said some will be transmitted.
Yeah.
Alright. But let's say that the original. The incident. Plus. The transmit or the reflected. Be equal to.
I have one question, do I should do.
Oh god. Yeah, hold on. Let's call this
Start OG.
let's, yeah. OG, let's call this one, this is still gonna be one for medium one, and then this will be medium two. But this will be reflected in medium one. Okay,
Yeah,
and so the sum of these have to be whatever comes in to here. Similarly, we can say. So on this side, we have the parallel component, on this side we have the parallel component. So we can say something like, let's write these in terms of. The transmitted wave will look like that, there it goes. Okay, so why did this become negative while this is positive? Well, that's because we have a V going back in the opposite direction. And now we have these two nice equations. See if we can show them. We call this one, we call this R, we call this two. We're just gonna notice that there's a similarity there. And we're gonna multiply the whole thing. We see the presence of mu naught V naught, or mu naught, sorry, mu one V one. So let's multiply that everywhere. So that will give us, this, write this function, E1 equals C over N one, 2, C over N2. And just like we wrote it up there.
are we trying to solve this like a system of equation?
Yeah, we have two equations, two unknowns. So you can now solve for either one of these. There's also a helpful little formula for something called beta, which should be mu one and two over mu two. Okay. And you can solve that system of equations. Promise you. It's not that hard, but I'll let you do that at home. Because I don't want to do it. Every time. Okay. So we can say something like E of R equal to 1 plus 1 minus beta. 1 plus beta.
That, we've seen that before, that's. That's like definitely something we talked about.
Yeah.
Yeah. Don't worry about it. We're not gonna know what it means yet. Okay, you've never seen it before in any other class. Okay. And we can say something along the lines of E that is 1. That's of all of these. All right, let's see if we understand what. So generally speaking, the permittivity here, U's are gonna change less. Sorry, the polarizabilities are gonna change less than the permittivities. So the ability for a material to be electrically polarized is usually much easier than the ability for that same material to be magnetically polarized. Because we want to think about generally how that works. Okay, charges are free to rotate. Maybe they're free to move around. But not, speaking generally, not all material is magnetically susceptible. Right, so the reason why we have magnetization in the first place is either from electrons, spins, or from electron orbits. And those can be fixed in a lot of cases. Okay. So generally speaking, you might have these two be the same, and beta is like N1 over N2. That makes sense? So sometimes we can say that beta is just the ratio. This isn't always true, but sometimes beta is just the ratio of the speeds of light in both locations. Okay, so imagine for the first part that n equals 1 here and n equals 1 here. Does this give us what we expect? Right? If n equals 1 in both, then it's really not passing through into a different medium. So what should the reflected component be? Why does it have to be 0?
It's the same medium.
No, don't look at that. Don't think about it conceptually. You have a medium, you have a wave. Okay. Should there be a reflected component?
No.
No, there's no reason. There's no spontaneous reflection in our medium. Okay, so let's see if this is right. So beta was what? All right, so this is 1 over 1. So beta is 1. And 1 minus 1 is 0. Nailed it. Okay, what about this one?
Same, 2.
2. Oh, you nailed it. Awesome. Okay, now let's imagine some super unpermeable material. Let's imagine the world's greatest stopper of light.
Concrete.
Actually, concrete's not that good. You know why? Concrete gets hot. That means it is absorbing some light. It's not visible light. Okay. And in fact, the reason why you can answer your phone in class,
Concrete.
Bluetooth or Wi-Fi, these are radio waves going right through concrete. They don't even see it. It's completely, this room is completely opaque to radio waves. Or sorry, transparent to radio waves. Flying in, giving me all the texts. Hey, you need to be at work. Already at work. All right. So let's think about this one then. Super material that's impervious to all light. Let's say that N2, which is the speed. Okay. Let's see, what is this? N is always greater than 1, right? Okay, so let's make it really big. Infinity? Yeah. I was gonna say like 10. That's fine. That's fine. 10 over 1. All right. 1 minus b.
It's like -9 over 11.
9 over 11. How much is that?
Less than
0.9. Like 0.9-ish.
It's about 0.9. Okay, that's an astronomer in the back there. You know, order of magnitude is 1, and over here 2 over 11, which is
That's like close to.
it's like 10%,
Yeah,
right?
maybe 20%.
We're astronomers. Okay. So we have to, I mean, they need to add together to make sure that we get 0. But of course, I didn't do the math properly. Okay, so this reflected piece suddenly became huge. Because as we predicted, this beta, which is our measurement of how well light can continue, is also going to tell us how much is reflected back. Okay, so some property of the material, which says how well light is able to move at the speed of light. Okay, if you do a really bad job of it, you slow light down a lot, you then send a wave back from whence you came. and less of your original wave propagates in that medium. You see the implication?
So no line, so, or is it just like one time?
What do you mean?
Like, does it continuously do less light?
Okay, so I think your question maybe, and correct me if I'm wrong, you're saying like, let's say you have a packet of light. So the beginning of it starts to reflect, and then some of it starts to go in, and then does that as time, like, get rid of the whole thing. It's a uniform effect. So if we imagine one wave packet, it would then duplicate and make one go backwards and one go this way, but remember they're superimposed. So even though this one's coming in, it doesn't actually care or see about the one that's leaving. Right? Because waves can just whoop right through each other.
So it's like the opposite.
No. Yeah, okay, that's many weeks from now. Okay, does this process make sense? Okay. So for some folks, this is gonna be like the most annoying part of class. Everyone has a different part of E&M that they hate. For me, that was this. Because I definitely did not get how to like get all of these components to fit. It felt like arbitrary rules sometimes. But generally speaking, you want to come back to this derivation. So if you haven't seen that in chapter 7, I would strongly recommend it. This is how we think about the way that we have to maintain incidence at boundaries. And then generally speaking, we're just going to be doing stuff like this, varying the angle and then maintaining those same boundary conditions. Okay. There, okay, I already wrote that, that's fine. Okay. So let's now imagine the opposite situation. Let's imagine that N2 already did that. Oh boy, oh boy, oh boy. Let's do the opposite situation. Let's imagine that this medium here, N1, is smaller than no, the N2 is larger than N1. So let's imagine we have light inside of a denser, I don't want to say denser because it doesn't necessarily mean denser. Let's say we have light inside of water. Good. And here, air, maybe something. Okay. So light inside of air, light inside of water going into air. Now let's think about this for a moment. What is our expectation? Okay, that it's going to speed up. Very good. That's what the N does, right?
There's gonna be less reflection.
Less reflection. Okay. Good. All right. Let's think about this. Okay, so let's look here. Do these equations still work? So we could have N2V. What? Yeah, so let's have it be like 1.1 or something. This will be like. That's reasonable, right? Okay. So now do you have a reflected wave?
How big are the top and the bottom?
The bottom is bigger.
Yeah. So now B is small again. B is small here.
And if it's small, then I mean it's about the same.
It's about the same. All right. Reflection's almost complete, depending on how you look at it. And then here, only a little bit leaks out. Right? You've seen this before? You remember this total internal reflection? We'll see this in more detail when we hit it from an angle. Okay, you can have water, right? And you can shine a laser through the water, and it goes in the water fine. When it tries to get out of the water, it bounces back down in.
Okay.
Okay, so this is the type of framework that we'll be using. We'll derive it more in detail. You remember this? Yeah. In pure incidence, usually you can get the laser out. But this is an exaggerated example where you have 10, which doesn't happen. Okay, all right. So let's think about the amplitudes across the border. I want to give you like at least one problem so that you're not just all sitting there taking it in. We're gonna do this slightly out of order. Let's try problem 9.38. Okay, and we're gonna just set it up. Okay.
Over problem.
It will be, yeah. Always. All right. So here's the problem. Here's the problem. You have a fish. I draw a very good fish.
This is fish.
It smiles.
It looks like what?
Like who? You think Lucas?
I said it looks like a nuke. A nuke.
Oh.
All right.
Not here, pet fish.
Lucas.
Fish.
Really?
All right. So what is this?
It's either a really small fish or really big glass.
Okay. That's a very good point, but in fact, this is supposed to be an aquarium. However, maybe the glass is not to scale. Let's forget it for 1 month. Okay.
We're just really close to glass.
All right. So. Here's E, okay? Here's B. And here's B1. Okay? I have some amplitude E0 here. At this boundary, I would have some V1, but it's minus. Okay, I'm gonna have some reflected E. Now B is gonna be going in that direction. This E is going in this direction. Right? So this is my E original. And then this is my E reflected. Okay. Then 1, 2, 3. Now the problem is going to ask you for a lot more, but let's just start off by seeing if we can understand some of the basics. So show me, if you start with light emanating from the fish, imagine it's a beautiful radioactive fish, okay? Now it sends off some wave, and it's moving in the kx direction. Okay? So at each interface, show me how the wave is going to be labeled. Now, I don't want you to write E to the IKX or anything like that. Just see how I drew these pictures, right? At each step. Whether there's new velocities, whether there's different orientations to V, E, and B. Does that make sense? That's what I'm looking for. Does that make sense?
You said there might be a different orientation. Just like a telescope, but flips in.
I'm not saying that. I'm saying, well, you notice that B started, so the V was originally going this direction.
Yeah.
And B was going up and B was going this way. When B hits the boundary and reflects, E doesn't do anything, it stays up, but B now has to go in the opposite direction. We saw that with this piece over here. Is the reflected part starts with the same size magnitude, but 1/V. And since V changed sign, then B has to change sign. Okay. So first draw what the wave will look like on this side, and then any other part that you may see. We'll just spend a few seconds. We got it. Alright, it's first. Okay, so let's maybe write some letters here, so we'll call this Z equals 0. We'll call this Z equals the thickness or the depth of the window, which accurately points it out, and this is a small fish. It's a massive aquarium. Okay, so on this side, E is coming out with V2. Everyone have that? And E is gonna have some transmitted component in section 2. Okay. Let's do some, we'll do it like this. An initial component in section 1. Does that look too much like a 2? Or we're good? And then what happens on this wall?
Yes.
Okay, so this will be negative V2, and this will be called E reflected, good, in region 2. All right, so let's be a little more clear here. Let's write this as E R in region 1. Good, and then well,
We're gonna see like the same form of it, but just like now,
yeah, so in this picture here, for the ET, how does the first one start?
like the right hand will get E and E. But
Like
now
E's up,
they're transmitted up.
this one's
V
V2,
2,
Is B still that way?
V should still be that way.
is still towards us, right? This is ET, right, on the left hand side?
So just to clarify, it's the fact that there's some that went through the incident with no problem that we're seeing it in the same form.
So if we're thinking of, and this is not the right hand, we'll write this clearly my left hand, right? But it happens to be the right orientation. Okay, going in the direction of Z. E and B still going in the direction of Z, so they're heading in, they hit this surface with normal incidence. And we don't really know how much this is gonna change. Maybe these two will both become smaller, but they're still going in that direction, so they still maintain their same orientation. Whereas if they hit this surface, they do a flipsy-do, right? And so now they're headed back this way. And it's still E, still pointed up, but B is now pointed into the board. See? Okay, so we can always use this hand to determine our orientation. Because light is always gonna propagate like that, as long as you use the same letters. You do this, get it backwards. Okay. All right, here, how does the B field look?
It's gonna point the other way or into the board then.
All right, on this side?
Same setup as what we're seeing now. There's gonna be a transmit.
What do I?
Oh, V3, sorry.
It's been 3.
Yeah, good. So now I have E transmitted 3. Okay. And the problem's really gonna ask you for something which we haven't really talked about yet, but it is trying to ask for how much transmitted light in total are you gonna get? All of it. So to do that, you'll need to couple each one. You'll need to start here, right? Through the boundary conditions, and then you'll have a system of equations that gets you how big ET2 is. And then that ET2 will have one reflective component and ET3. So then you'll work backwards from ET3 all the way back to the E original, right? And then you're done. Alright, so let's see how we would do that in practice by going one step backwards. Okay. So. Energy is gonna be conserved. Okay. We said something about, pointing vector was like as. We said that on average, it transported a certain amount. So we can call this word, the average pointing vector, the intensity. And this is gonna be equal to 1/2 epsilon V E0 squared. Okay, also called your I for your intensity. If you've ever seen I before, this is how we calculate it. And I'm not going to read you the derivation, it's still just as valid as when we originally did it, but you'll notice two major differences here. E is, or E0 is now E appropriate to the material that we're in, and V is the speed of light in that medium, whereas before we had C. Okay. Okay, so let's use an assumption, because it makes everything easier. Love that assumption, so nice. Okay. Generally speaking, R, the reflection, or sorry, the reflected fraction is going to be the intensity of the reflected light over the intensity of the incident light. That's just how you define it. Does that make sense or no? Okay. And you'll notice that some of these pieces are going to drop out. And some of these pieces are going to stay. The 1/2 will be on top and bottom. And the epsilon V, these are going to be changing depending on where you are. Wait, hold on a second. I and R, are they going to be changing? What do you think?
It depends on like that.
Let's have a look here. Let's look at this picture. You tell me. Yeah, why not?
This is just the glasses changing.
Well, where is IR, the reflected one? The intensity from the reflected one. Which
Oh, it's
location?
still in the same medium.
It's still in the same medium.
Okay,
So since it's in the same medium,
no problem.
then the intensity doesn't care about the speed of light changing or permittivity changing. So it's the same top bottom. So the only thing that's changing here is this piece. So I can just say. That, right? Okay, and then we're gonna have something else called the transmitted fraction. Okay. The transmitted fraction will be the intensity of the light going in versus the intensity of the initial light. Okay, and ideally you add those two, and you would get what? If I add R plus T,
It's 0, right? That should
the
count.
reflected fraction plus the transmitted fraction
One.
should be 1.
Oh, okay.
So if 30% was reflected and 70% was transmitted,
Some of it.
then I should get all of the original light back. So this one says how much reflected intensity was of the original, and this one should say how much of the transmitted was of the original. Okay, so now do I have to worry about these ones? The epsilon and the V's?
Yeah.
Yes, now we do, because it's a new medium, new speed, all of that garbage. So we're very upset. And so we say epsilon 2 V2 E transmitted squared. That's the original one. I'm gonna forget the 1/2. Epsilon 1 V1 E original squared. Okay. And the most important one So there is a really fun derivation. That you can see over here. When we set these things, B's and betas. If you set mu naught equal to mu2 equal to mu1 equal to mu3, you set them all equal to each other, and write beta in terms of the ends. You can write beta in terms of the ends, you can write your reflected and your incident in terms of ends for the different mediums. So in fact, these ones simplify dramatically. I'm going to show you that at the beginning of Tuesday's class, but if you want to, you can look ahead it. You can just see that to calculate this, you don't even need this. You don't need this. You don't need these. You barely need these. You just need the ends of the medium. If I give you something as simple as it's water, it's got 1.75. You can just be like, well, it's 1.75, take the ratio, square them 4, and then you're done. Really remarkably powerful. That makes sense. Okay. Any questions before we adjourn for today? All right, you're very excited now. Now it makes sense again, right? None of this stupid median stuff.
This was probably about conservation.
Yeah, entirely, right? So this is just power per unit time. You can't lose it, right? Some of it's got to be reflected, some of it's got to go through. And you know, when we think about scattering, when we think about doing your computer game modeling, it's this all the way through. How much is reflected, how much is scattered, how much is transmitted at every medium interface. Right, so if you have some, you know, nice lake in Red Dead Redemption, it's the top of the lake, right? How much is reflected? You don't model that properly, it looks like Stardew Valley. I love Stardew, don't get me wrong, but it's not accurate. I don't think anything looks like that. You can't get mad at me for that, that's a true statement.
Don't diss my Stardew Valley.
What's that?
Don't diss my Stardew Valley.
I'm just saying it's not photorealistic. That's I would absolutely never, I've logged plenty of hours. Okay, any questions, folks? Okay, bye.
I